there are lots of developments of ways of improving or enhancing convection, particularly in pipe flow, and lots of manufacturing processes have been attempted, including having corrugated tubes, having internal fins, having some of the pipes actually twisted so that we generate turbulence to make sure that our boundary layer is not very effective, and consequently we improve our overall heat transfer coefficient. This has particularly been used in the last few years, particularly in hot water systems, in domestic and commercial hot water systems and heat exchangers. You find, for example, at the moment, some of these instantaneous hot water systems running on gas or electricity are quite small in size. One of the reasons for that is the use of some convection enhancement in the tubes that make up the heat exchangers between the source of heat and the water flowing inside it, with the view of reducing the size. And of course, reducing the size also means reducing the cost and enabling the system to use a smaller space. And all these are important in real engineering applications. So this is a relatively old slide, but it shows you how we can improve the H value by up to, in this case, 60 or 70 or 80% using some of these interesting and different sections of the tube we are dealing with. And obviously we have to strike a balance between the more complex manufacturing process and the reduction in size and cost to reach a compromise, and this compromise could very well depend on the specific application we are dealing with. And these are some more results, and here again we are looking at the Nusselt number and the friction factor for various types of shapes of fins inside the tubes. Any question before we go to the next part? So now we have finished dealing with internal flow in tubes, and we go back now to external flow for the cases of where we have a number of cylinders or a number of pipes, and we have the flow going across those cylinders or shapes. So it's external flow, but it's again relating to flow in cylinders or in pipes. So let me just make sure you know what I'm talking about. So for example, if we have these particular shapes, whether they're circular or square or other shapes, and we have the flow coming from left to right, what is the heat flow between that solid boundary? And this solid boundary could be a cross-section of a pipe where another fluid is flowing, or it could be just a solid particular section. So we're looking at flow across these, or more importantly, and I'll show you another diagram in a minute, more importantly, if we have a case of a tube bank where we have lots of cylindrical shapes with the fluid coming across them, and this is quite a common application in, for example, shell and tube type heat exchangers and other heat exchangers where we have external flow going around a number of banks of tubes with the aim of obviously doing the heat transfer between the fluid in the tube and the fluid outside the tube as quickly as possible, or as cheaply as possible, and using the least possible bulk or volume. So this is the next part, which in a way combines both internal and external flow. And this table gives us a number of situations. So the first equation is when we have a single cylinder, one single cylinder, and the fluid is flowing across it. So we're dealing with this cylinder, especially if I can draw it better, it should be a circular cylinder in this case, and we have a fluid going past it here. There's obviously a temperature difference between this surface and the bulk fluid coming across. So the equation associated with this is simply the Nusselt number, and again here we have to go back to the film temperature, which is the average between the wall and the bulk temperature. So the Nusselt number equals C, a constant, times the Reynolds number defined in terms of the diameter of our cylinder. So this is our diameter. And using the film temperature, so using the film temperature to find the properties and the diameter of the tube or the cylinder, the Nusselt number equals a constant times the Reynolds number raised to the power n times the Prandtl number raised to the power 1 on 3. And the value of C and n is not a constant. It depends on the range of the Reynolds numbers we're dealing with, and these are the values to be used. So you can see from very slow laminar flow to quite high turbulent flow, we have varying values for C and N. So if we have air or water or oil moving to heat up or to cool down a cylinder across, we use this equation, and it's quite straightforward. Then we'll deal with the flow across a family or a number of rows of cylinders in a minute. We'll then, if the cylinders are non-circular, again we need to do something about it. Flow across spheres, if we have a sphere, and this could be, I don't know, a low temperature gas in a spherical tank being hit by hot air. We want to know how much heat is lost to the cylinder from the outside air. And these cylinders have to be kept at low temperatures. We can work that out using the appropriate equations. And then we have tube banks, which we'll be dealing with. And also we can even deal with the case when we have liquid metals flowing at high temperatures, where the properties become a bit funny, particularly the Prandtl number, and we have special equations for these. And some of these equations you will see in a minute, and some you have to go back to the textbook to find. So this particular table, this particular plot is for the Nusselt number associated with a single sphere. So we have the flow across a sphere. We work out our Reynolds number, and we can work out the Nusselt number, which is h bar d divided by k. Here we have the flow across a number of different non-circular cylinders, and as you can see here at the bottom, we even have, it's a bit difficult to call this a cylinder, but it's just a plate, and the air or the water is flowing at 90 degrees to it. But if there is a temperature difference, we can work out the Nusselt number based on the C and the N using the same equation that we had previously. You know, that equation. Nusselt number equals C times Reynolds number to the N times Prandtl number to a third. So the C and the N are given in this table based on the ranges that are being shown here. So we have to satisfy that the Reynolds number is in this range and then we can use the value of C and N to find our Nusselt number. So, one of the particular practical applications of flow across a single cylinder is what we call hot wire anemometers. Has anybody heard of hot wire anemometers? Does anyone know what an anemometer is? No? An anemometer is a device used for measuring speed, air velocity or water velocity in a particular application. It's a very simple device which we can hold and place in a particular spot, and that helps us measure the air or water or oil velocity, and it's used a lot inside machinery where we can get a digital readout of the temperature. And we do that, of the velocity in particular, but we do that based on the heat flow between a thin cylindrical shape and the air flowing around it, or a plate flowing around a liquid. So in this case, we're talking about a platinum wire, and we use platinum to make sure it doesn't corrode over time. So a thin platinum wire, 6 millimeters long and 25 microns in diameter. What we do here, we obviously use a small device so that it doesn't interfere with the velocity distribution inside wherever we are trying to measure the temperature and the velocity. So in this case, we have air at 20 degrees Celsius, and we want to measure the velocities which range between 6 and 30 meters a second. The way we do this is maintain the temperature of this wire at 230 degrees Celsius, and we adjust the current that we need to maintain that temperature, and by reading the current we can work out the velocity. As you'd imagine, the faster the flow, the more power that will be dissipated, and that's how we do it. The only thing we need is to make sure that we understand how much heat is transferring between that thin anemometer and the air surrounding it. So we need to use the heat transfer equation, the Nusselt number equation, which we saw, which is C times Reynolds number raised to the power n times the Prandtl number raised to the power a third. And in this case, we know that our temperature difference is, well, our hot wire temperature is 230, and our air temperature is 20 degrees. So we can work out the film temperature, which is the average between these two. 230 plus 20 divided by 2 is 125. And this enables us to evaluate the thermal conductivity and here the kinematic viscosity. We need to go from a range of 6 meters a second to 30 meters a second, so we need to look at both of these. So at 6 meters a second, we have a Reynolds number of 5.64, and at 30 meters a second we have a Reynolds number of 28.2, and in both cases we can find the value of C and N from the table that we saw earlier. And once we've done that, we can say that H times the surface area equals, we work that out. So we find our C and N, as you can see from this table that we saw a little earlier, and this enables us to find the value of H. So this, the term on the left is H times D divided by K. That's the definition of the Nusselt number, and that enables us to find H, and Q equals H times A times the temperature difference, and this gives us, if you like, a generalized equation for Q, the amount of power, electrical power that we have to feed in to our anemometer. And this equation enables us very quickly to find the value of U regardless of the velocity. So we measure Q and we use this equation to find the U infinity, the air temperature that we're looking for. So from a digital measurement of our current, and obviously voltage is usually constant, we can work out our U infinity, and that's a lot easier than the other physical direct measurement of velocity. Any questions? And please keep that in mind. If you see an anemometer being used, you know how it works now. We simply heat up a small probe and measure the energy, the electrical energy, to keep it at a particular temperature, and this tells us what the velocity is. Obviously, if this is going to be used at higher velocities, we'd need different values for C and N in our equation. This last equation won't be the same. Well, we're always talking about heat flowing from a hot surface to a cooler fluid. So it depends. If you want to look at it from the point of view of the wire itself, you can say it's negative, but the equation, heat is usually not a vector, if you like, in this case. Right, so this is the single sphere. And now we come to, again, as I said earlier, quite a practical or practically significant situation where we have a number of rows of tubes, and these tubes could be 20 or could be 200. And these tubes are in a vessel where we have flow across them to try and transfer heat from a hot fluid to a cold fluid. Obviously, one is inside those tubes and one is outside those tubes. And this is, I guess, the nearest you'll get to your assignment situation. This sort of situation is found in things like boilers, in things like what's called shell and tube heat exchangers, and many other applications where we, as I say, fill a whole shell with a number of parallel tubes like that, and let the other fluid, well, one fluid inside the tubes and the other fluid outside the tubes. In this diagram, we've got two types of arrangements. We have the parallel rows of tubes, as you can see at the top, and the staggered arrangement of tubes, which is meant to give better mixing of the fluid, as the fluid in the middle gap between adjacent tubes in row 1 have to hit the center of the tubes in row 2 and so on. So hopefully we get better mixing in the second case, and this has certainly been found in practice to be a better arrangement if we have a choice. And again, the major equation that we use is this Nusselt number using the film temperature equals a constant times the Reynolds number raised to the power n and the Prandtl number raised to the power third. The only thing to remember is how we calculate our Reynolds number. Our Reynolds number in this case is obviously in terms of the diameter of the tubes, the film temperature, and also we need to remember the velocity to be used in this case is the maximum velocity occurring in that heat exchanger, which is telling us that we are looking at the velocity between the gaps as opposed to the velocity here. Here we have a larger area. Oh, for our heat to be flowing. Sorry. If we look here, that's a big area for the flow. What we need is the velocity in this location where we have the minimum flow area or the maximum velocity. And these are some applications, as I said, of the type of heat exchangers we're dealing with, which we need to be considering. So in this case, we need the value of C and N. And you can see in these tables a number of variables that we need to think about. So first of all, we have SP on D. So that's the spacings along or parallel to the flow between one center of the first row and the second center of the second row. So SP is the distance between centers of pipe along the flow direction divided by the diameter. So here we have a choice of these gaps being 1.25, 1.52, and 3. And then also we have Sn, the normal gap between centers. So the gap between centers of pipes across the flow direction, not along the flow direction. So that's Sn on D. So once we have determined Sn on D and Sp on D, then we can find the value of C and N and put it in our Nusselt number equation. And you can see here we have two different tables, one for the inline and one for the staggered values, to enable us to find the Nusselt number. And once we find the Nusselt number, the rest follows. And also in this table at the bottom of this slide, if we have a small number of rows, we have to adjust for the Nusselt number value, because these equations are correct once we have more than 10 rows, or 10 or more rows to be more precise. Looking at the time, I think I'm going to leave you to do this example. And what I will do is maybe give you a minute or two for a breather,